We'll give this one more try. How did the homework go? Okay.
That arc tangent with the like square root of 1 minus x over 1 plus.
Oh, yeah. Yeah, that's a lot of algebra in that one. You gotta be kidding me. What the hell's going on, man?
Yeah, it's just like the first part's okay, but then you have to do the whole, like you have to isolate the
All right, I'm feeling pretty doubtful that this is going to work. The technology sucks sometimes. I know you're eager to ask me a question. Hold on. Okay, I give up. This room is just cursed. All right, I had a nice little visual thing to show you, but oh well. Okay, what was your question? Is this something I can do quickly, or is it looking at a solution to a problem? And
it was an example 5 that he asked us to do.
Okay.
I was in a tutoring lab and I had it checked by 2 tutors, and they said that my answer was correct. But I compared it to another student's answer, and it was completely wrong because I overlooked something.
Okay, I'll look at it after. Do you have time after? Or maybe like a minute or two, I'll just look at it. Okay, yeah. Anything else? It seems so quiet in here. What's going on? All right, so let's get started today. I don't have the lecture notes to go off of, but that's okay. I mean, we actually don't have a lot of, there's only one page for the lecture notes for today. So it's not a whole lot of material. So we're doing 3-6. 3-6. So 3-6 is titled Hyperbolic Trig Functions. All right, so I had this nice little visual thing, but I guess I'm just going to have to do this without my computer. So I grabbed this dirty thing out of the back of my truck, and let's see. You want to volunteer? Sure. All right. So here, just grab that end. Do you want that end? That okay? So just hold it up anywhere you want. Come this way a little bit. All right, right there. Okay. So if I take this like that, and we look at that right there, that shape, right, looks like what to you? It looks like a parabola, right? What did you say? Oh, okay. So a parabola, maybe it's part of the arc of sine, maybe, right? So we try and figure out, is there a function that would represent every single point on this curve, right? Now I could, stretch it out like this and it would change, right? But it still kind of has a general shape. So the question becomes, is this a parabola? Or is this some arc of a sine? Or is it something else, right? And it turns out that, we can move this around, but there's no way we could ever come up with a parabola that would land on every single point here. It would be impossible. You might get the parabola to land on a few points, but this is not a parabola, and it's not a sine curve. Okay, that's all I need. So the question is, what is it then, right? So you see, you drive down the road and you see these power lines, right? Stringing the power from tower to tower, right? And the lines, you know, they have to sag. It's impossible to have them completely taut. So they have to sag a little bit. And these are very heavy lines, aren't they? I mean, this cable, it's pretty heavy once you talk about like a 400, 500 foot span maybe. So it would be interesting for us to know what the force is that's being exerted on that mount right here, right? How much force is being exerted there. And to do that, we need to kind of know what this angle is, like what angle it's pulling at. And to find that angle, how could I find the angle right here of this line, of this curve? How could I find that angle? What could I do? What could I use to find that angle?
Angle of down from that point.
Yes, I guess. That is the angle, I guess you could say, kind of like the last problem we did at the end of class. But I'm just saying, like, from what you know in Cal 1, yes, go ahead.
Would you take maybe, I guess, a straight line and then the lowest part of the drip?
Okay, so like here, and then what?
And then make a triangle out of that?
And then run it from this point to this point? So that would give us like a hypotenuse, right? From here to here. Is that the angle of this curve at that point?
Take the inside part of it?
Okay, this one right here. But is that the angle of this curve? Let me draw it. Okay, so let's say we have this tower, right? And we have this curve hanging like this. From this point, the curve hangs down, comes back up like that. So I think what you're suggesting is perhaps we take the middle point, draw a hypotenuse like this,
Cross the other way from the bottom?
and then, okay, so you'd create a triangle here, like that. And then you're trying to find this angle right here,
Just the underside?
this right here, right? Like from here to here, is that what you're saying? That angle?
Just the left side of it?
Okay, but how do you find just the left side? You're saying just that angle. Okay, but that's what I'm saying. How do you find that angle? I mean, I agree you could draw a right triangle, but this angle right here that opens up like that on the triangle is not the angle we're looking for. So what do you think you could do to find this angle? Any other suggestions?
Angle of the tangent line.
Okay, so that is where we want to go with this. So look at this right here. I'm going to take this out. If I were to take, let's say, this point right here and take its tangent line, that'd be pretty close to the angle, wouldn't it? But the exact angle would be if I went to that point and found the slope of the tangent line there. That would give me that angle. Now, it would be a slope, and then I would somehow have to get an angle from that. But it would be my hypotenuse of my triangle, so to speak. Make sense? So to find that angle, I need to take the derivative of this function, but what is the function, right? It's not a parabola, it's not a sine curve. Well, it happens to be a hyperbolic trigonometric function, and it's actually what we call cosine hyperbolic. But that's kind of one of the like motivations of what we're talking about here, okay? That's something you could see like a useful application of hyperbolic trig functions. Right, so we'll get back to that problem. I'm going to do a problem at the end of class where we actually find the angle of a cable suspended from a wire. But let's first define the hyperbolic trig functions. All right, so sine hyperbolic of x, that's the way we write it. So you could either say that that's sine hyperbolic of x, or if you'd like, you could say that's hyperbolic sine x. It's your choice, all right? And the definition, we need to maybe go back and look at what was the definition of sine. Like what was the definition of sine x? Did we have a definition of sine x? Yeah, we created that function. There are two ways we created this function in pre-cal. One of them was by looking at right triangles and saying, okay, sine is the opposite over the hypotenuse. And then we generalized it and we said, okay, if you have some point sitting out here, and you have a radius here, and you have an angle here, then sine of the angle, theta, is equal to, this is x and this is y. Anyone remember? I mean, it's the triangle, right? It's y over r, right? Still the same thing. But what I'm getting at is there were two ways in pre-cal we developed the idea of sine. Right triangle, and then just a point sitting in space. Either way, we had a way of defining it, right? Okay, now how do we define sine hyperbolic x? It's very strange when I put it up here, you'll see. It's e to the x, all right, it's an exponential function, right? Minus e to the negative x over 2. So it's some weird algebraic construction with exponential functions. So e to the x is one that we've seen before, right? What does e to the x look like? Looks like that, right? That's e to the x. What does e to the negative x look like? It's reflected over the y-axis. That's e to the negative x. All right? And somehow, if we combine them in this way, by taking e to the x, subtracting this one, and then dividing the whole thing by 2, we get the hyperbolic sine function. All right? So that is the definition of the hyperbolic sine. Now, whenever we define a function, you may see this later down the road. If you put a colon in front of the equal sign, that means we are defining sine hyperbolic to be this. That is our definition of that trig function. All right? So let's get right into asking what the derivative of this would be, right? Because, I mean, this is calculus. I just gave you a function. It's a new function. And we like differentiating, right? So what would the derivative of this be? So if I asked you, what is the derivative? Well, you know what? Let's wait on that. Let's do cosine hyperbolic. We'll do the sine hyperbolic derivative in a second. Let's do this. I am now defining cosine hyperbolic to be those two, or that expression. What's the difference between sine hyperbolic and cosine hyperbolic? Addition. All you have is an addition sign here. So it's the same expression, except subtraction here and addition here. So the way that I remember that is I just say, okay, I have to remember the e to the x, the e to the negative x, and divide by 2. I just think s subtract, and that's how I kind of remember the sine is the one that gets a subtraction. Okay, and then what about tangent hyperbolic x? Yeah, fortunately for us, it's the same as what tangent was back in pre-cal. This is sine hyperbolic x over cosine hyperbolic x. So you would take this and divide by this. This and divide by this. So what would happen if we did that? What if we took this and divided by this? Let's do that over here. E to the x minus e to the negative x over 2. And then I would divide it by e to the x plus e to the negative x over 2. And division is really like multiplication of the reciprocal, so I can just like flip it. Yeah, the 2's are going to go away. Right, like that. And then these don't cancel, right? You can't do that. So you have e to the x minus e to the negative x over e to the x plus e to the negative x. That would be your hyperbolic tangent function. Okay? Now, there's something else that we could do with this. I'm going to just write it down, and I'm going to see if anyone can tell me what I did. This is the same as this. So what did I do there? How did I get from here to here?
You separated the numerator from the denominator so that you cancel each one out.
How do you mean? Like this over this, this over this?
Yeah.
That's not quite what I did. Maybe you could get there that way, but that's not quite what I did. What does, what? I multiplied by 1. I multiplied by 1. And let's see what happens here. When you distribute, what's e to the x times e to the x? It's e to the x squared, right? It's e to the x squared. And then what do you do when you have something to a power to a power? Multiply. So that's 2x. So that's this. And then what's this times this? Well, you add the exponents, don't you? Negative x plus x is 0, so you get e to the 0, and that's 1. So you could almost look at this like this is really 1 over e to the x. It's almost like we cleared the fractions out, right? Okay, so this is an expression for tangent hyperbolic, and that one up there before I did that was also an expression for tangent hyperbolic. All right, we good? All right with that? Okay, now, again, I'm going to hold off on the derivative for just a second. What are some properties of the hyperbolic? Now, there's three more, right? There's three more, which would just be the reciprocals of these, okay? So I'm not going to put those up here. Some properties. Now, let me remind you off here on the side some of the properties from pre-cal. Do you remember this property? Do you remember what we called that property? Or this one? Yeah, this is what we call the odd property of sine. Sine was an odd function. Plugging in a negative value is the same as plugging in a positive value, but then changing it to negative. And with cosine, if you plug in a negative value, it's the same as plugging in a positive value. We call this the even property. Do y'all remember these from pre-cal? I mean, you remember seeing them at some point? Odd and even properties. And then we also had some other really nice formulas in pre-cal. Remember that one? Of course you remember that one. Pythagorean identity. Okay, so we have properties with our original trig functions. And now we have a new group of trig functions, right? We are introducing 6 new trig functions. They're the hyperbolic trig functions. And the question is, what are some of the properties of these? Do we have even and odd? What do you think? Let's try this. Let me put the property down here. Sine hyperbolic of negative x. I wonder, is that equal to negative sine hyperbolic x? What do you think? Do you think it will be? How would we check? This is kind of a question. It is the property, okay? But how would we check to see if that's true? We take sine hyperbolic, and we replace x with negative x. So let me do that over here. So sine hyperbolic of negative x is equal to e to the negative x minus e to what? Positive x. So all I'm doing is replacing this with negative x, this with negative x. The negative negative becomes positive, and I've got this, and then over 2. So is this sine hyperbolic? Is this? Not quite, right? This is positive, that's negative. Over here, this is, they're switched, right? So it's negative, and this is positive. So it's off by a sign, isn't it? So we could say that it's equal to negative sine hyperbolic x, right? I guess you could pull a negative out here and then change the order. Yeah. Okay, so I just pulled a negative out here. That's this. I just kind of flipped them over. Do y'all agree that this is the same? And then this right here is sine hyperbolic x. Okay, so it turns out, yes, that sine hyperbolic is odd, and then I won't check it, but it also turns out that cosine hyperbolic of x is even also, right? So just like it was with our in pre-cal, right? But what about the Pythagorean identity? You think the Pythagorean identity holds? Do you think sine hyperbolic squared x plus cosine hyperbolic squared x equals 1? I mean, it seems everything else is held up so far, right? Maybe? Well, unfortunately, it does not, okay? But what we do have is this. Cosine hyperbolic squared x minus sine hyperbolic squared x does equal 1. So this property holds. But when you add the two, you do not get 1. You have to subtract the 2. And remember with subtraction, the order matters, doesn't it? So it has to be the cosine hyperbolic first, squared minus the sine hyperbolic squared. If we do that, we would get 1. How could we check that? If we wanted to verify that that identity was true, how could we do it? We could square them and subtract them, right? Do y'all want to do it or not? You don't want to verify it? Okay, so let's do it. Let's square this. This will be some fun algebra. Actually, I'm going to erase because I need a little more room.
Is that like cosine 2u?
Cosine 2.
Double?
It's not double angle. Are you saying does it hold?
I mean, it looks like it, doesn't it? Isn't that what, like, for trig functions, isn't like cosine 2 theta? Can't you rewrite that? Isn't that an identity?
There's 3 different ways to rewrite that. Yes, but that would not be the same as what I just put up. Because there's no 2x in there. There was no 2 anything in that formula.
Yes.
You know what I'm saying?
Yeah.
So like with that one, in that equation, cosine 2u, you have 2u in the argument, and that equals, and there's 3 different things it could be equal to. All of the things that it's equal to has just x in the argument. So the arguments change. Here with that formula, the argument's the same, okay? All right, so let's try this. Remember what we're trying to verify. Cosine hyperbolic squared x minus sine hyperbolic squared x equals 1. We're kind of asking, is that true, right? So let me square cosine hyperbolic. So when I square the top, I have to do that, right? And when I square the bottom, I get 4. And then let me subtract from that e to the x minus e to the negative x squared over 4. All right, let's just see what happens. I'm gonna factor out a 1/4 just to get that out of there. Is that all right with you? And then I'm going to square this, right? Square that. E to the x plus e to the negative x times itself. All right, and we're just going to get to play with some exponents here. What's this times this? E to the 2x. Okay, this times this? 1, right? E to the x times e to the negative x is e to the 0, because you're adding the exponents. E to the 0 is 1. Got that? So we got 1 there. And then what about the inner ones here? 1 again, right? So plus 1 again. And then what about the outer ones? So it'll be e to the negative 2x. Agreed? And it's plus. So plus e to the negative 2x. All right, that's what happens when we expand this one out. And remember, we've pulled the 1/4 out, right? So let's square the other one. The only difference is it's going to be minus and minus, right? So what's the first term we get? Oh, and also, be careful, we have a minus sign here, right? So that minus is going to distribute to everything we get here. So what's our first one? E to the 2x. What are the next 2 that we get? Be careful. That's 1, but it's minus 1, isn't it? Because this was a positive, this was a negative. So we get minus 1. This one right here, minus 1 again. And then the last one, so minus and minus, we get a plus this time, plus e to the negative 2x. And then all of that's in brackets. So do you see what happens when I pass this negative through here? When I pass the negative through, this becomes minus, this becomes plus, plus, and this becomes minus. And then lots of good things happen here. Gone, 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 gone. And we get 1 plus 1 plus 1 plus 1, which is 4. And what's 1/4 of 4? 1. Okay? That makes sense? Yeah? Okay, so there are several other formulas. They're located on page 185. I don't want to go through them, but I just want you to be aware on page 185 at the bottom, they call them the hyperbolic identities. And they have a sum. Remember the sum and difference formulas for sine, like sine of x plus y equals, and then something, and cosine of x plus y. There's some of those are presented to you. All right, so just be aware of them. Questions?
Are these on our formula sheets for the test?
These are on the formula sheets. Yes, I'll verify that. But on the formula sheets, at the top it says like reference page 1, reference page 2. So the hyperbolic trig functions are, I know they're here. I've seen them. Reference page 4, about midway down, is the hyperbolic functions. It has the definitions.
Can we use any other reference pages on our test?
Yeah, the formula sheets online on Canvas, I believe, are like the first 5 or 6 pages of those reference pages.
Okay, I think I only saw like one.
One page? No, there should be, yeah, it should be like a couple.
Okay.
Yeah. It stops, though, intentionally, it stops. Once it gets to the antiderivative formulas, the table of integrals, it stops at number 20. It does not continue because there's actually 120 formulas in this book in the back for integrals, but I'm only allowing you to use the first 20 on the tests. Thank you. Okay, now, can I move on to derivatives? We understand now that we have 6 new trig functions. They have a bunch of properties and identities just like our regular trig functions had, and now we're going to define the 6 derivatives of these. So if there's any justice in the world, right, the derivative of this should be cosine hyperbolic x, right? The derivative of this should be negative sine hyperbolic x, right? And the derivative of this should hopefully be like secant squared hyperbolic x, something like that. Doesn't turn out that way. All right. So sometimes it's good, sometimes it's not. What is the derivative of sine hyperbolic x? All right. Well, this should be pretty easy to do. Let me do something here. Does everybody agree with me that this in here is the same as this, right? I just pulled the 1/2 out. Yes? Sometimes it's easier to write it this way, and in some books you'll see it written this way as opposed to this way, right? And in calculus, when we're differentiating, we always like to pull constants out if we can anyway. So this is kind of a preferred way of seeing the formula for me. The book does present it this way, but just be comfortable seeing it that way also. Now, if we take the derivative of that, the 1/2 is just going to come along with us, right? Because it's a constant out front. Then we just differentiate each of these. So I'll put parentheses. What's the derivative of e to the x? E to the x. And then I have minus. Now, what's the derivative of e to the negative x? Yeah, it's negative. I didn't write the negative, but there it is. Negative e to the negative x. So it's the derivative of it is itself, but then the derivative of what's up here, which is -1, which is why you get that negative right there. Okay, we good? And now this is 1/2 e to the x plus e to the negative x, and well, what? That's cosine. That's cosine hyperbolic, right? That's this. So far, it looks good, doesn't it? It looks like it's doing what sine and cosine did in pre-cal. All right, let's see when it stops doing that. How about we do the derivative of cosine hyperbolic? I so feel like I'm forgetting something. I am recording. My microphone is on. Oh. The what? Yeah, I don't know. It's weird. I feel like I'm missing my security blanket up here or something. I need my whoopee.
Realize you left your stove on at your house.
Yeah. That's a nice thought. No, I remember unplugging. Okay. So we're doing this one, right? So the derivative of this, derivative of this would be 1/2, and then e to the x again. And then here, because this is a plus and we know we're going to get a negative out of it, it's going to become this. Right? That's sine. That's sine hyperbolic. No, we're not off by a sign, right? Like remember, derivative of cosine of x is negative sine x. But the derivative of cosine hyperbolic x is just sine hyperbolic x. There's no negative. So you just got to remember that. And then also, you know, this class is about integration, right? So when we go backwards, right? If I ask you right now, what is the antiderivative, or, you know, what would take you back from cosine back to where it came from? You would say what? Sine, right? The antiderivative of cosine would be sine. What would be the antiderivative of sine? Sine, not this, sine. Antiderivative of sine of x would be what? Negative cosine x. Because you have that sine. We'll get more into that. But here, when we integrate or differentiate, it's always going to be positive. We don't have to worry about that sign. It doesn't mess us up, which is nice. Okay, what about the derivative of tangent hyperbolic x? So I want to take the derivative of tangent hyperbolic x. What are we hoping it's going to be? Secant squared hyperbolic x, right? That would be, we would be really happy to see that. So if I'm taking derivative of tangent hyperbolic x, I'm taking a derivative of this, right? And then I can apply the quotient rule. So the derivative of the, and this all depends on how you learned it, but the way I teach my students quotient rule, I do derivative of the top times the bottom minus the derivative of the bottom times the top, and then all over the bottom squared. So I'm going to do derivative of the top. What's the derivative of sine hyperbolic x? Cosine hyperbolic x times the bottom. Okay, and then minus derivative of the bottom is just sine hyperbolic x. We don't have any negative to worry about. And then times the top, sine hyperbolic x all over bottom squared. Right? I'll put squared there like that. Right? Do you recognize the numerator? Cosine squared hyperbolic x, or cosine hyperbolic squared x, however you want to say that, minus sine hyperbolic squared x. What is that? It's 1. We just proved that, didn't we? Isn't that numerator 1? Yes. Okay. So 1 over cosine hyperbolic x squared. And the reciprocal of cosine hyperbolic should be secant hyperbolic. So we've got it. Okay?
Is that considered Pythagorean, the numerator?
Actually, I do not believe so. Because the Pythagorean identity does come off of the geometry of a right triangle, and that's what the whole Pythagorean is about. This geometry is a lot different. I mean, there is a geometry with cosine hyperbolic and sine hyperbolic, but it's not based off of the right triangle. Don't know if the book goes into that. Yeah, they don't get into that, but it's not called, I do not believe it's called a Pythagorean identity. It'd be weird if it was. All right. So we've done the derivatives of sine hyperbolic, cosine hyperbolic, tangent hyperbolic, right? And then we have the reciprocals of these. So we have cosecant hyperbolic, secant hyperbolic, and cotangent hyperbolic, and all of those should have derivatives, right? So those derivatives are contained on page 186. And those, again, are on your formula sheets. So I guess if you were to summarize what we've done here today, is you walked in, I mean, you may have seen this already, but I'm assuming most of you walked in and you had your 6 trig functions from pre-cal, right? And you knew their derivatives. And then we talked last class about the 6 inverse trigonometric functions, right? Arcsine, arccosine, arctangent, all those. And we talked about their derivatives. Those are all on your formula sheet. So now we're working with what? We had 6 from pre-cal with the 6 derivatives. And then we had the inverse trig functions. There were 6 of those with the 6 derivatives, right? So now we're up to like 24 functions, kind of, yes? Now we have all the hyperbolic trig functions, all 6 of those, and their 6 derivatives. Yes? What comes next? The inverse hyperbolic trig functions. Right? Now, we don't get into a big, long treatment with those because we're not going to use them now or in the near future. So I just want you to be aware that on page 187, they talk a little bit about the inverse hyperbolic trig functions, and then they give you the formulas for them. All right? I'm just show you where one formula comes from. That's it, just one of them. And then they talk about the derivatives of those. So do y'all understand that there's still another 6 inverse trig functions, hyperbolic trig functions out here, and 6 more derivatives? And they're all on your formula sheet? Okay. So let me define now the inverse hyperbolic sine function for you. And like I said, this is the only one I'm going to show you, and then we'll talk about its derivative. So sine hyperbolic inverse of x is equal to, check this out, natural log x plus square root of x squared plus 1. There we go. That is the definition of the, that is just stupid. I don't know why I did that. See what I did? Okay. Yeah, that should be negative. Sine hyperbolic negative 1 of x. Is it surprising to see the natural log here? Is it surprising to you to see the natural log? No, because it's the inverse of sine hyperbolic. And sine hyperbolic had e in it, right? So the inverse of e is natural log. So it makes sense that we should see a natural log, but I actually want to show you how you can get this, because I think the algebra in here is worth seeing. A lot of you, I would venture to say 90% of you will probably have never seen something done the way I'm about to do it. It's pretty cool. All right, you ready? There we go. I want to prove that that's true. All right, so do you remember sine hyperbolic of x equals, let's call this y. Y is equal to sine hyperbolic of x. Do you remember in college algebra how to find the inverse of a function? There's like a systematic way of doing it. Go back to college algebra. Okay, yeah, so the first thing you do is you say, okay, I'm going to switch x and y. Does this sound familiar? You switch x and y and then solve for y. Okay, so if I rewrite this, sine hyperbolic y equals x, and then try and solve for y, what do I get? What can I do here? So I switched the x and y, the positions. Now I need to isolate y. I need to get it by itself. Okay, so there's two things we could do here. You could do arc sine on both sides, but the problem with that is what would you get? Y is equal to sine hyperbolic inverse of x, and that does not show me that it's equal to that. It just says, yeah, y is the inverse hyperbolic trig function, whatever it is, right? Don't know what it is. So this doesn't quite get us there. So the way you can do it is by rewriting this side. I think that's what you were saying. We're going to rewrite this side of the equation using the definition of sine hyperbolic. So wouldn't this be, I'm going to write it this way, 1/2 parentheses e to the y minus e to the negative y equals x? Isn't that sine hyperbolic of y by definition? And now you get to solve for y. And this is what I wanted to show you. How in the world can you solve that for y? Okay, I like that. Multiply by 2. That makes some things better. Okay, so introduce a natural log. So that this is kind of in some way giving away the fact that we're going to need natural log, right? But I'm going to put it up here, but don't write this down because it's not going to work. Natural log on this side, natural log on this side. All right, let's say I did natural log on both sides. Can you do anything with this? You cannot. Because you have natural log of two things being subtracted. Had these been multiplied together, we'd be okay. Then we could use properties of logs and maybe split it up. But because there's subtraction, we have two terms, we can't do anything algebraically with that. Do you see that? So that's kind of like, not really. I do believe a natural log will come, but it's not time. So I'm willing to try anything that's algebraically valid. Sir, you all right? Are you not interested? You have an idea here, maybe? The table's open here. What?
Raised to a power.
Say that again?
Multiply by e to the y on both sides. Like we did.
Would that be a legal move? Multiply, sorry, you may not have heard. Multiply both sides by e to the y. Okay, now what would the value of that, what would happen? So, because we always want to foresee before we do something what would be happening when we do it. So if I hit this with e to the y, what would it become? E to the 2y, okay. If I hit this with e to the y, what would it become? 1. And then over here I'd have 2x times e to the y. So I'd have a new expression, but I'd no longer have that negative exponent. Is that worth exploring? Okay, we can do that. So multiplying both sides by e to the y, we get e to the 2y minus 1 equals 2x times e to the y. Y'all good?
Just raising to the power of 10, would that have like, doesn't that cancel e?
The only way to get rid of e is to have e to the natural log of something. And you can't just, you can't raise, when you have multiple terms like this, you can't, it wouldn't work. Because even if you like squared this, right? Even if you like squared it, but natural log is not a number, it's a function, so it just wouldn't work that way. All right, we're following you down this road now. But I will tell you that is correct. That's the first correct step. So did you have any reason why to do that? I mean, we did it last time, right? So that's the way a lot of times math works. You know, you've done something like this before, you try it, and you see where it takes you, right? But this is really the point at which I said most people have never seen this before. This is kind of where we're at. So unless someone has some brilliant thing to do, I'm going to just lead you down the road the rest of the way. Move the 1 over. So you want this one over here? Okay, I'm okay with that. I'll just put it on the end. Is that all right? I'm guessing you wanted to do that so you could do natural log now, or no? No? Okay, so could I do natural log on this side and actually get something good to happen? Yes, because now natural log of e to the 2y should just be 2y. So it looks like you're starting to get y by itself. Problem is, you still have y over here. So when you do natural log on this side and you have addition between these, you still can't split them up and you're still stuck. You see that? So that's not going to work. Let me write down what we should do next, and maybe I can force the idea from somebody. Okay, this is the next step. It's a quadratic. All right, so look, I want you to think back about quadratics. Most of the time in your life, when you've looked at a quadratic, right? We said a quadratic equation has an answer, right? Could be imaginary, but basically we have a formula for this, right? X is negative b plus or minus all that junk. But A, B, and C have always been numbers, haven't they? And the x has always been the variable in the problem. Yes?
Wouldn't it be -1?
Did I not? Yes, thank you. I did not bring that over right. Yeah, because we had moved it over, hadn't we? Okay. All right, so where's the quadratic? It is quadratic, but what's the quadratic? Like, I'm confused. E to the y is like the x over there. I'll put it in parentheses even though I don't need it. Do y'all see that? Like if you look at this as kind of like the x over here, you have like x squared, and then this right here is like the b, isn't it? And the b actually has a variable in it. And that's really not something we normally ever saw, right? Like letting b be a variable. But we can still do it the same way. So if you're keeping score doing that, it's like our a and our b and our c are what here? So what's the a for us here? It's the number in front of the thing being squared. So the a is 1, b is what? Negative 2x, and c is negative 1. Y'all see that? And now we just use the quadratic formula. The quadratic formula says that the solutions to that are x equals, and then the quadratic formula, right? Here, it's going to be e to the y equals, do y'all see that? Instead of x, we're saying e to the y equals, now we do negative b plus or minus b, so blah, blah, blah. So what's negative b? 2x plus or minus the square root of b squared, 4x squared, minus 4 times a times c. So 4 times a times c, negative 4, right? So it's really going to be plus 4 here. And then all of this over 2 times a, so 2. All right. Do you see that 4 underneath the root on both terms? Factor it out and then pull it out of the root. And when it comes out of the root, it will be a 2, won't it? And that won't all the 2's cancel then? So I go e to the y equals, that 2's gone, this 4 is gone, it came out as a 2, so it's gone, it's gone. So all you have is x plus or minus this root of x squared plus 1, right? And now the last step is to take the natural log on both sides. See, now we have, y is isolated now, right? We finally got y as a single term. So when we take natural log on the left, we get y. When we take natural log on the right, well, we get the formula. With one exception. That says plus or minus, and the formula said what? Plus. So why can't it be minus? Why can't we have minus here? Natural logs can't have negatives in them, right? And when we look at the expression x minus square root of x squared plus 1, if we ever did that, do you agree that this, whatever you do here, is always bigger than x? Why? Well, because that right there would be x. So if I add 1, it's bigger than x. So this is bigger than that. So this is always negative. And so that's not possible, so we chunk it. That's it. There's the formula. You can derive all of them that way. Yes?
Would it have been wrong to do like u prime over u?
Where? Well, we didn't do a derivative.
Oh, wait, over?
We were just trying to, I was just trying to prove to you, yeah, just trying to prove to you that the arc sine, the definition of the, inverse hyperbolic sine is this. That's the definition of it, okay? Now, what's its derivative? You take the derivative of that, it would be derivative of natural log of something, so 1 over this times the derivative of what's inside. And that is sitting there on page 188. They have the derivatives of all the inverse hyperbolic trig functions. Okay, we're doing good. Y'all feel all right with that? that's some pretty neat algebra. It's nice to know that the quadratic formula works for that. Let's do that pole, the problem with the pole, okay? So I need to first define something. Remember I started class by hanging that cable thing I have? So So when you hang a wire between two poles or a rope between two poles, the shape that it makes is called a catenary, right? That's the shape. It's not a parabola. It's not an arc of a sine function or cosine function. It's catenary. And in general, all wires hanging from poles can be modeled with this function right there. So here, A is not 0, and C is an element of the real numbers. That just means C is a real number and A is a real number. So you can plug different values in for A and C, and it's going to change the shape of the catenary. So A has the biggest impact. If you change this A, you remember when we had the thing and we pulled it and it changed the shape? That's what A does. A changes the shape of the hanging wire, and then the C just moves the whole graph up and down. All right, that's all that does. So in general, this is the model for it. So now let's suppose that we have a wire hanging from a pole. I don't want to do this problem because it's a homework problem. So I'm just going to kind of make up my own.
Are we going to have to find the y-intercept for this, like, to see where the tangent line, like, intersects it?
Well, yeah, let's see. We'll see. Yeah. Okay, so let's say that we have, man, I really don't want to do this one. All right. So here's an example. We have catenary modeled with y equals, let's go with 30 cosine hyperbolic of x over 30 minus 12. It is suspended between two, see how tall I want these poles. Two poles which are 16 meters apart. So just keep in mind here that x and y are in meters here. All right, so the idea here is that we've got a catenary hanging between two poles, like this, and that the distance between the poles is 16 meters. And I didn't give you the height of the pole, did I? Okay, and I'm not going to. All right? And we are going to assume here that this right here is 0. In other words, this is like the x-axis and the y-axis. So the center of the catenary, right, the lowest point is going to be going right at the y-axis, all right? So I need to tell you that this picture is modeling what's happening, all right? So here's the first question. Find the slope of the curve where it meets the pole. So we'll call this part A. Find slope of curve where it meets pole. So what does that mean? Interpret that question. What is the math that they want me to do here? We talked about this earlier. Tangent line, right? They want the slope of the curve where it meets the pole. So where does it meet the pole? Yeah, there's two different places, right? Here or here. So let's go with this one, all right? Because it doesn't specify in the question. So we want to find the slope of that curve right there. And I heard someone say, and that's 8, isn't it? That x value is 8. Because if you're 16 meters apart, and I told you it's hanging right through the center, then that should be 8. So isn't this really asking us to find y prime at x equals 8? Right? That's what it's asking for? All right, so what is y prime? What is the derivative of this? All right, so we have a 30 here, right? So it's just going to come for the ride? What's the derivative of cosine hyperbolic of something? Sine hyperbolic. No, we don't have the negative, right? It's just sine hyperbolic of the x over 30. Are we done? Yeah, now the derivative of the inner function, the argument of this cosine hyperbolic function. So the derivative of that is what? What's the derivative of that? 1 over 30. So times 130, 1 over 30. So that completes taking the derivative of this, doesn't it? Now we have minus derivative of 12, which is just 0. And look, those 30s cancel, don't they? That's nice. So we have sine hyperbolic of x over 30 is y prime. But we want to know what the value of that would be at x equals 8. So just plug 8 into this. Do we have any questions? I'm going to keep moving here. Do you all have any questions on this? All right, so let's plug in 8. So at x equals 8, y prime would be equal to sine hyperbolic of 8 over 30. And we're probably going to need a calculator at this point. Now, some of your calculators actually have the hyperbolic sine function built into it, but I'm not going to do that. What I'm going to do instead is I'm going to use the definition of sine hyperbolic, which is 1/2 e to the 8 over 30 minus e to the negative 8 over 30. I mean, isn't that the definition of sine hyperbolic of something? All right, so on my calculator, I'm going to try and do this computation. And you try and do it on your calculator, and let's just see if you and I come up with the same results.